I could get rid of the root x. I agree. Algebraically, if I'm going to let u be that, I agree that u squared would be x, okay? There's no, I don't see an x over here though, right? But believe it or not, this is going to work. All right, so let's just, this is one of those problems where it does not seem like it's going to work, but it's going to work. All right, so let's stick with this right now. I'll come back to this because this is actually helpful too. It's cool to see something on this. So for now, I'll put that on the back burner. If I do this, the derivative of this is 1 over 2 root x dx, yeah? Okay, now if we go to try and rewrite this integral right now, I know I'm going to be able to replace that root x with what? With u, right? Root x, that's going to be my u. So I'm going to have something like this right now. E to the u, but then I have to replace my dx. So solve this for dx? Yes?
Yes.
Okay, so if I solve that for dx and I just get this by itself, I have to multiply by 2 root x on both sides. If I do that, I get 2 root x du equals dx, right? Now, initially, it looks like that's a problem because your dx is going to be replaced by this. This still has x's and u's in it, doesn't it?
But can't you replace the square root of x?
But because that's root x and root x is u, I can replace that root x with u. It's kind of like we got lucky. You like this one more? Well, we'll talk about how that's going to work in a second. Are there questions on this, though? I'm going to replace this with u. See, you have to understand that when you go to replace dx right here, what you put in there cannot still have x's in it. It has to just have u's. It's okay to be off by a constant, but here we're off by more than a constant. We're off by an entire function. But we can make up for it because it just so happens that the substitution we made is right here. So let's replace dx with 2u du, and we'll pop the 2 out now. We cannot pop a variable out of the integral. Boy, life would be real good if we could do that, but we can't. So this becomes integral, I think I'll put it up here. This becomes 2 integral, what's still here? E to the u and then u. I'm going to write it this way, u e to the u. I'm only doing it that way because maybe it'll help you see, because we've done a few like that now. Yeah, now we're going to do integration by parts. We're going to have to use the w again. This will be the w, this will be the dv. When I differentiate that, it's going to go to 1. When I integrate that, that's going to be pretty clean. Questions? Okay, now I want to address, this was brought up also. I told you that we can actually use this to get to the same result, to the same integral up there. Let me just show you how it's done. If we agree that we're going to replace u with root x, that's the same as saying that u squared is x, yes? Now what I'm going to do is I'm going to take the derivative on both sides of the equation implicitly. So what is the derivative of u squared? It's going to be 2u du, and then equals derivative of x, which is dx. And look at this. It's the same thing. Isn't that kind of cool that it works out that way? So, but, you know, why would you have squared this? I'm not quite sure why you would have just done it, but it works, which is nice. All right, let's do the table on this. W here, dv here. What's my w? U. My dv then, there's only one choice, right? E to the u du. And then complete the table. Differentiate down, dw is du. And integrate up, you get just e to the u. Don't let me forget that 2 this time. So at this point, I can use the formula. It's going to say that this is equal to this times this, right? But there's my 2 in front. Since it's becoming two things, I should use a bracket. So 2 u to the u. And then minus integral e to the u du. That's my diagonal, right? And that integrates really clean. Antiderivative e to the u is itself. So I'm going to get 2 u e to the u minus 2 e to the u plus c. I went ahead and integrated that, got e to the u, and I went and passed the 2 through. Now we have to replace u. And u is root x, right? So we have 2 root x e to the root x minus 2e to the root x plus c. You could factor out a 2e to the root x here, couldn't you? I mean, I'm just pointing it out, you could. All right. I want to check this one. This one looks pretty clean. I've got a product rule here. Okay, so if I take derivative of this, it's going to be derivative of this times this plus derivative of this times this, and then minus just derivative of that. So what's derivative of root x? Just root x. 1 over 2 root x, but then if I hit it with a 2, it's just 1 over root x. So I'm going to have 1 over root x times e to the root x plus, now derivative of e to the root x, which is itself, times the derivative of what's up here, 1 over 2 root x, finish off product rule, times this, 2 root x, right? And that finishes up product rule in that first piece. Minus 2 times derivative of e to the root x is e to the root x times 1 over 2 root x. And do you see it? Let's see, what happens here? These are going away? Okay, so we have 1 over root x, e to the root x, minus 2, oh, those 2's can cancel, right? So we get minus, what did I forget? Where?
E to the x plus e to the x, negative or square root of x. Did that get canceled?
Hold on, let me keep going. This is not looking very nice, is it? E to the root x over, not over, times 1 over root x. What's that? That looks like 0, doesn't it? What did I miss?
Plus e to the square root of x. At the very top, there's 2 of them, and you only drop 1 down.
Sorry, feels like Friday right now. There's 3 terms, yes. Oh, did I not? Oh, I didn't put it. Oh.
No, just add an e square root of x.
Okay, so this one right here is this one, right? Okay. These went away, so I have plus e to the root x. Oh, there, okay. Duh. Stupid. All right. E to the root x. 2's went away. We still have times 1 over root x. And then this cancels with this. I was like, oh, shit, we're getting 0. And so we get what? E to the root x, which is what we were supposed to get. All right, the fabric of the universe was starting to fall apart there for me. Huh? Part? What? I cussed? I did cuss. No, I didn't say 10. No, I did not say 10. I never said 10.
I actually want this point.
We're gonna need, someone's gonna need to go check and see.
You said 10.
Gladly.
Scouts on it.
All I know is you said it twice
So
already.
that's 23.
All right. Y'all don't want that many extra points.
Yeah.
All right. Someone go find that, I guess. On your formula sheets, I let you have reference pages 1 through 6, right? Those are the ones that are on Canvas. No, wait, is it 1 through 6? Yeah, 1 through 6. Those are the ones on Canvas. Those are the ones you're allowed to bring to the exam. No more than that, right? You can't bring your own favorite unit circle from pre-cal or anything like that. That's the only pages you're allowed, right? But if you actually have the book that nobody tore the rest out, there's actually a reference page 7, 8, 9, and 10. So the integration formulas on your reference pages stops at formula number 29. That's on reference page 6. That's the formula it stops at. But if you were to look at the rest, it actually goes to formula 120. And one of those formulas in particular is kind of cool to look at. Actually, there's nothing special about it, but I'll just show you. It's formula number 73, and it says this. If you're trying to find the antiderivative of sine, I'm going to do it just like it is in the book. Sine u du, so sine to the n du, that the answer to this is negative 1 over n sine to the n minus 1 of u cosine of u plus n minus 1 over n, and then integral of sine to the n minus 2 of u du. Okay, this is what is known as a reduction formula. And this formula is good for n bigger than or equal to 2. So if you plug an n that's bigger than or equal to 2 into this formula, it will work.
Do you want to write this down?
Nope, I don't want you to write it down. I'm showing you this formula, all right? So I want to show you how you would use a formula like this. Let's say somebody wanted you to do, as an example, the integral of sine to the 8th power of u du. You would say, hey, I think there's that reduction formula I was shown that one time. And you would come to this and you would say, all right, well, n for me in this problem is what? 8. So according to this formula, this should be equal to negative 1/8, right? Sine to what power? 8 minus 1 is 7 of u, cosine u, right? Plus, now what? 7/8 integral sine to the 6th u du. So what you've done is you've started with an integral that had sine to the 8th power, and we've concluded that this antiderivative is this plus this new integral. Now, what can you tell me about that new integral? You could do it again, right? This is sine to the 6th power. So couldn't you apply that formula again to this? Like use this formula again with n being 6? And when you did that, you would have, from this? You would have two new things, right? Can we just imagine that there's a bracket here, okay? Inside this bracket, what would be in there? So just start it all over again with n being 6. Negative 1/6 sine to the 5th u cosine u plus 5/6 integral sine to the 4th u du, and then you would close the bracket. So this right here would be sitting after the 7/8. And then that you could do again.
That'd be a really long final answer.
Yeah, so you see how we would have like a formula within a formula within a formula. Do you see why they call it a reduction formula? Every time you're doing it, you're reducing the power, right? And eventually you get it down to where that last integral is doable. Understand? No, now you're asking like, do I need to know this? Can I copy it down? The reason I'm showing you this is because I want you to know where this formula came from. So
What shows?
how can we prove a formula like this? Or where, was there some like book under some rocks somewhere in a cave that we stumbled upon and it's like, man, look at all the math formulas in here. Like, we don't know who came up with these, right? But man, they're awesome. No, right? These are all made by human minds, right? So what we're going to do is we're going to generate this formula right now. And it may seem like, whoa, how in the world are we going to come up with something as crazy as that? But after you see it, well, let me leave this here. Integral, blah, blah, blah. Do you have any idea what I'm going to use to do this? Just looking at that right there? What you think I'm going to use? Like what technique I'm going to use?
We're gonna use like integration by parts.
Integration by parts, because doesn't integration by parts turn an integral into u times v minus integral v du? Yeah? So it looks like someone used integration by parts to get this. Let's see it happen. So I'm going to come in here, I'm going to start this problem out right here.
Isn't it just like integration by parts like over and over again? Because it like all the signs.
It's only one application of it. You only need it one time. And that's what gets you the formula. All right, so let's start with this. And before I start setting up my table, just tell me if you agree with this. Is this the same as this? Yes? So what I've done is I've said instead of saying sine to the n of u du, I kind of peeled one sign off. And that brought the power of this one down by 1. Now, the reason I did that is because it's going to work this way. So somebody else already went through the mental torture of understanding that this is going to make it work. If you just try and do integration by parts on this, and you let your, we can't use u, if you let your w be this, you're not going to get to it. So that's what I'm doing instead. Let's look at this. Here comes your integration by parts table. You need a little more room. And I'm going to use w here, and I'm going to use dv here. Now, I'm going to choose my w to be this. All right? So that's going to be sine to the n minus 1 of u. And that forces my dv to be sine u du. Right? What's left? Now, I claim that if we do that, we will get the formula. We will get the formula I put on the board, formula 73. So let's see how it happens. Let's do this integration first. I think that integration is the easiest thing. V would be negative cosine u. Good. Okay. Now the derivative of this. So as something to kind of get you thinking, if I said, hey, everyone, take the derivative of sine to the 7th power, you would use chain rule. 7 would come out first. Sine to the 6th, you'd reduce the power by 1, and then chain rule would tell you take derivative of what's down there, cosine u, right? That would be the derivative. Keep that in mind. Let's do the derivative of this. The derivative of this would be, what comes out front? This power right here, which is n minus 1, right? I'm going to put that in parentheses, n minus 1. And then it would be sine raised to the n minus 2, right? Because I have to subtract 1. It's already got 1 taken away, so it's going to become n minus 2 u. And then, not du yet, cosine u du. Do y'all see that? All right. Now that we have the table, let's see what the integration by parts formula would give us. We're going to do this times this, right? So how about this? Negative sine to the n minus 1 of u cosine of u. Agreed? That's this times this. Minus integral, and then I'm going to have my diagonal, this and this together. So minus